Hey, okay. So, we will hopefully get there today. Okay, we'll try to wrap up network flows. So let me quickly remind you exactly what the framework was, so that you can get back into the game. You are given a directed graph. You are given positive weights on edges. You are calling these capacities. Cu to V. These are not symmetric, so you can have a large capacity going one way and a small capacity going the other way. So, for example, something like that. You are given a source node. You are given a sink node. And the question being asked is, what is the maximum flow you can send from the source to the sink? Okay, this is exactly where we were last time, or this is how I set things up last time. Okay, so the first thing we realized was that the single source, single sink problem is not different from the multi-source, multi-sink problem, simply because you can have several sources all getting a feed from a single super source, all the sink nodes getting a sink with a super sink, and essentially you put enough capacities on these links so that these do not become your constraint. It is also very clear that you cannot send infinite flow through a flow network, assuming that all your capacities are bounded. Right? So, all you need to do is essentially a simple bound would be to take every capacity, add them all up, and say that that is the maximum. Why? I am claiming that I will take a graph, I will look at all the capacities, simply add them all up, and I am claiming that essentially that cannot be exceeded in terms of a flow. Can you think of a quick argument why? I give you a graph, it has got all these capacities to it. I am trying to find a quick upper bound on the total flow that I can send through the network, and all I do is I calculate all the UVs, CUVs, sum them up simply. And yes.
The flow is the total capacity. The flow is the addition of all the flow in each edge. For each edge capacity we equal the flow.
A slightly smarter argument. Okay. So, the reason you are not being able to argue this is because we have not defined exactly how we are going to have a mathematical expression for flows. And soon as we have a good mathematical expression for flows, it is very easy to see this thing. Okay? Otherwise, what simply happens is that you have capacities going every which way, and you are probably trying to think of a flow that can meet exactly what I said, but it is very unlikely that you can, because I am also adding the flow, the capacities what looks like on the opposite direction. And so, the way you want to set up the flow is to have simple expressions that tell you exactly what the flow through a network is. Okay, otherwise, the question that I just asked you is likely to be difficult for you to answer. Soon as we get a good expression for flows, you will find out that it is very easy to answer this question. So, the way we went around defining a flow, and mind you, when I say a flow, I do not mean the maximum possible flow, just a flow. Okay. So, the fact that I am managing to send something from this source node to the sink node has to be one constrained by the capacity itself. Okay, so, that is called the capacity constraint. Which essentially says the flow from U to V is less than or equal to the capacity from U to V. And this is the only expression that actually involves the capacity itself. there are two other things we talk about flow which essentially makes this thing a very beautiful structure, and those are the skew symmetry, which essentially says that flow from U to V has to be the minus of the flow from V to U. Okay? The only time I will allow you to define something to be a flow is when you satisfy this constraint. So, for example, in this case, if you are sending a 3 on this side and a 1 on the other side, that seems to be a valid flow, except that I will not allow you to claim that to be a valid flow. If you send a 3 from this side, it certainly satisfies the capacity constraint. If you send a 1 on this side, that too satisfies the capacity constraint. But because in this particular case you are saying it's a 3 this way and a 1 this way, it does not satisfy skew symmetry, I will say this is not a flow. And the reason I am claiming that this is not a flow is simply because I am saying that you can simplify this. Instead of saying 3 and 1, take out whatever is the case where which is going back. So, if you are sending 3 that way and a 1 this way, you are essentially sending 2 that way. So, I will say flow of U to V is 2 and not a 3 this way and a 1 that way. And just by saying flow U to V is a 2, I will assume that flow of V to U is a minus 2. It is a peculiar concept. Okay? It is not natural for you to think this way. It just turns out that if you do things this way, and remember, this is for the example where I am sending 3 out of a 5 there and a 1 out of a 1 there. I am claiming that you can always simplify, and once you have simplified, you have a single flow really going from one side to the other, and I want you to see the skew symmetry as simply a mathematical equation that tells you that something going this way to me is the same as the negative of that going the other way. For all you care, you just need to leave the positive flow out there. The negative flow going the other way is natural because of skew symmetry. Is that making sense? This is the most peculiar concept in this whole thing. This is what allows you to solve a lot of things. Okay? It is not natural, but soon as you assume this to be the case, that these are the definitions, immediately what happens for you is that a lot of things get taken care of just by running through the algebra. It is one of those very few examples where just closing your eyes and doing the algebra actually gets things done. Is this making sense? Do you understand this concept here? Okay. So, because you have skew symmetry, you can now throw in flow conservation. And flow conservation simply says that except for the source and the sink, every other node has a sum total of 0 flow, by which we mean that going from here outward is 0. All that essentially means as whatever is coming in will have a negative sign assigned to it, whatever is going out will have a positive sign assigned to it, and therefore, when you sum the whole thing up, you are going to get a 0. So, apart from V minus S minus T, apart from these nodes, if you have a node, then summation of F from that node to the rest of the graph. Okay. So, you fix this node, you run through all the other nodes in the graph, you sum them all up, and you are going to get a 0. And this is the case only for nodes other than the source and the sink. And once we have this, we simply claim that the flow through the network is simply so you pick the source, stick it up there, add up all the flows going out, and that will be a flow, because everybody else has a 0. Only the source, when you sum things up, will give you a positive number that is defined as a flow. Okay. So, this is a constraint that you have in your head. This is a very peculiar thing we just introduced. This allows us to tell this and immediately allows us to say that. And now you can clearly see why the upper bound argument can be made very easily. I claim that the maximum flow you can send through a graph, and now you are thinking conceptually the liquid going through the graph. I said that the maximum flow you can send through a graph is the sum total of all the capacities in all the edges, simple upper bound. It immediately follows from this. This one essentially says, look at all the capacities going out of the source node. Those flows, each individual flow cannot be greater than the capacity going from the source node, and there you go. So, if I sum up all the capacities, they certainly include all the capacities going out of the source node, which simply is going to be an upper bound on the flows through those edges, and therefore, I have an upper bound. Okay? What I am trying to point out to you is that sometimes having a very peculiar concept helps you everywhere else. Immediately you can prove things. Is that making sense? How many here do not get it? How many get it? Okay, good. So, last time I was trying to show you something else that just pops out of this whole thing. And I am trying to prove that this, which is by definition that, and mind you, whenever I put a capital letter someplace, I mean a set, and when I mean a set, this is a mnemonic. It essentially corresponds to the following. You sum over all those. So, F, S, comma, whatever is that. If I were to then put some other capital letter here, I will have a second summation. Okay? So, it is essentially sum over all elements in either this location or that location, depends upon whether you have a singleton or a set. Okay? So, we know that this is by definition, but what I am trying to prove to you is it is also, so you have the source from which you have the flows going into every network, and the claim is it is exactly what comes out of the sink. This too is difficult to prove conceptually. If you want to prove it conceptually, you have to talk about exactly where things are going, where things are coming out. You might get confused. If you just look at these constraints, it becomes immediate. Once again, a simple mathematical definition that allows you to do things very easy. So, we can quickly prove this one. So, what I am going to do first is fill it in. Okay, so, I am going to say F VV. Okay, so, I add a lot more nodes out here, and then I take those out. Does it make sense? Okay, so, I am just saying that this is a singleton, this is a set. I am going to fill this up and make it a set, and then remove all of those guys. So, I have made it a set, and then I have removed all of this. This I immediately claim is 0. I claim regardless of this set you take here, so long as the set is sitting on the right side, it is going to be a 0. Why? I am using skew symmetry. Regardless of the set, I could have had anything out here, so long as that is repeated on the other side. Skew symmetry says that by symmetry, for every one of this kind, I will have the negative of the same kind sitting. Okay, so, that leaves me that. And once again, because of skew symmetry, if I flip these two guys, I can remove the minus sign. Right? F u to v is minus of f v to u. So, if I flip these two, I'll be able to take the minus sign out. So, essentially what I am saying is that this is that. In my head, I am trying to show this. Right? So, now I have to play with this guy. So, I am going to take t out of that. So, I am going to split this up into f v t plus f v minus s minus t. Okay, I take the singleton out, and so that is the remaining. this is that. So, I need to simply show that this is equal to 0. And the way I show that is I essentially flip this over. This is minus of f v minus s minus t v. Okay, I've just flipped these and put a minus sign in. And now I claim that that I know is a 0. Why? Is it because of symmetry? I mean skew symmetry. Now, why is this 0? Flow conservation. For every element here, I have a capital V. So, I just open this up one step. I say that this is essentially for every u, capital V, summed over. And I know that those u do not include either the source or the sink. And each one turns out to be a 0 by flow conservation. So, the entire thing is a 0. That allows me to say that this is what remains. Simple algebra. Close your eyes, you run through it, and you get the answer. Okay? This is the strength of that concept, having skew symmetry. And in fact, in network flows, the only thing that is a little confusing is the skew symmetry. Everything else is just natural. Okay, any questions so far? Okay, so now that we have shown this, let's introduce a new concept. Okay, so this is a very natural concept. Now that we have a definition of a flow, and remember, when I say flow, I don't mean the maximum flow. I simply mean a flow. The question is, if I give you a network and I say that there is already a flow sitting on it, is it the case that you can see that as a network which has some residual capacity in it, by which we mean that you take the flow out, okay, and that leaves you some in some of these links, and maybe leaves you nothing in some of these links. And the question is, can you build that network for me? Is that making sense? I give you a network which has some flow. So, I give you a network first, I then introduce a flow in it. And a flow is essentially anything that satisfies this. Okay, I close my eyes, I just produce a function f which is between any pair u v, it gets a number, I just go and check and make sure that it satisfies all of these things. It is surprising that that produces a flow for me. So, I do not have to carefully say I am going to take the 3 and split it up into 2 and 7 here and then take that and then move it here and here. I will do none of that stuff. I will go to every node, I will just make sure that these are all satisfied, and that will be a flow. Once a flow is given, it basically means that if you have a capacity of 5 and you already have, say, a flow of 2, it means that you can still probably send 3 to it, through it, maybe. It might get stuck someplace else. Now, the question is, can you take the 2 out and leave that residual network for me, so that I can work with just that residual network? Why am I trying to do this? Because the algorithm that we are going to define is an incremental algorithm. Of all the algorithms you have seen so far, when I ask you, find me the best something, you just go churn, 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 best comes up. In this particular case, what we are saying is that to produce the max flow, one way of solving it, and it turns out that there are other ways of solving it. One way of solving it is to incrementally throw in flow after flow after flow, or rather increase the flow slightly. If I want to increase flow slightly, what I need is a mechanism that allows me to start with a flow and add a flow on top. Do you see that? I do not want a capacity, a previous flow, and a new flow. That makes it too complicated for me. I cannot talk about the previous flow and the new flow so that they all add up to satisfy things. I do not like that because it makes things cumbersome. So, what do? I say capacity, give me an initial flow. Instead of adding a new flow on top of this flow, the first thing I will do is I will produce for myself something called the residual network. This is essentially what you are thinking of, the capacity with these flows taken out in some sense. Then on that new network, I am going to add a new flow. That is going to be as simple as the previous situation, because it is almost like a network with nothing going through it, except that you already know that you have something going through it which you have deducted from that. That is the technique we are going to use. Is that making sense? Okay. So, if that is the case, it turns out that the residual flow is very easy to define. Once again, because of skew symmetry, all we will do is we will say that the capacity for a given flow already in your network, the residual capacity from u to v is simply going to be the capacity minus the flow. Mathematically, this is exactly what you would expect. You already had a capacity, and you took a flow up. The remaining sits there. Except that because of the definition of skew symmetry, things become very different from what you think it was. Okay, so let me show you an example. Here is a link, and I have a capacity of 5 on it. The very reason that I have not put the reverse link basically means that there is no capacity on it. So, it is essentially a link with a 0 capacity. Remember, I said to keep things simple, all 0 capacity links I take out. On this, I want to put a flow. Let us say that I put a flow of 3. Whenever I write things of that nature, I mean a flow of 3 on a capacity of 5. Okay, this is what I want to do. What do you think the residual network is going to look like? This is what you think is naturally the case, and yet what this is doing for you is a little more than what you thought it was doing for you. You are going to have on this side what you intuitively thought was the answer, which is essentially that I had a capacity of 5 and I have a flow of 3. So, I take the 3 out of the 5, I am left with a 2. However, this has a capacity of 0, and you have to keep applying this everywhere. The claim is apply this all through the graph. This had a capacity of 0. If it continues to have a capacity of 0, I am not going to draw it. But unfortunately for you, this has a capacity of 0 and a flow of what? A flow, because of skew symmetry, of -2, which essentially says 0 minus -2 is a 2. That on the right side is the residual network, assuming that I have done this for every pair. Why? Why is that happening? This is very natural. This is the residual, what is left, and I run it on this single link. It had nothing on this side, and the claim is that when I run this equation on this, I end up with a network that looks like that, 2 edges. One going that way, capacity. So, remember, this is the residual capacity, it had nothing to do with flows. This piece is a residual capacity. Why does it have a 2 going backwards? Why does it have a capacity of 2 going backwards? Yeah. Oh, sorry. So, yeah. Okay, so, the flow was 3, so the negative is a -3, 0 minus -3 is a 3. This has nothing to do with flows. This is a residual capacity network. It is almost like I am claiming that there is a pipe of size 2 here and a pipe of size 3 here. In this case, there was no pipe to begin with. I suddenly am throwing in a pipe, an extra pipe of capacity 3. I am saying that is my residual network. Why? Yeah. Exactly. So, it is actually accounting for the fact that there is this virtual pipe there, which corresponds to you being allowed to push 3 that way. How can you push 3 that way? You can push 3 that way by stopping the original 3 that you had pushed in the forward direction. It is almost like you have a virtual pipe going the other way. If this is too complicated for you, close your mind and just remember skew symmetry. Okay? What I am saying is that I am trying to stress on this beautiful construct that we have called skew symmetry that is allowing you to explore the issue. It is very uncommon in math that you produce a concept and that allows you naturally to realize many things. Okay, so just skew symmetry allows you this naturally. It is basically saying that if you stick to the rules, you will essentially get more than you intuitively thought is the case. In this particular case, when I am sending a 3, because I am allowed to stop the 3, that is almost like a virtual pipe going the other way, which is a 3. Okay, so here is a question to you. If I do not have any link between 2 nodes in the original graph, do you think that there is any residual graph, residual network, which will produce links for me? Why not? Repeat that. Capacity is 0 both ways. See, I showed you one example that soon as you have a single link, your residual network might have the opposite link. It depends upon your flow, of course. If I did not send anything through here, the residual network will remain this. But I can produce flows for which the residual network certainly produces itself a virtual link. I just want to find out, am I going to be able to produce virtual links any place? So, my question to you is that if in the original graph there are no links between 2 nodes, can I produce a flow that will produce for me virtual links? How many think no, cannot be done? How many think why? Yes, because the capacity is 0 and the flow is upper bounded by the capacity, this and skew symmetry. You see, skew symmetry is involved, because if capacity is 0, I could have a flow of -3. -3 is smaller than 0. Unfortunately for you, or fortunately for you, what happens is that if you have a flow of -3 this way, it means a flow of 3 the other way. That then gets constrained by the 0. So, the only flow you can have between 2 nodes which have a capacity of 0 both ways is the 0 flow. Once again comes from skew symmetry, because just capacity does not stop you. You can have a negative number which is smaller than 0. It is just that soon as you have that negative number, the opposite is a positive number that also has to be less than 0, and therefore, the only number you can get is a 0. Once you get a flow of 0 between 2 nodes, when you subtract a 0 from 0, you will only get a 0, and therefore, you will not get additional links. So, once again, because of skew symmetry, given 2 nodes which do not have any capacity between them, they will always remain without links with any capacity between them. You will not produce virtual capacities on them. Okay? But in any case, what is the maximum number of edges you can add to a network, because you suddenly produce for yourself a residual capacity network. So, I have a network, I have a couple of edges in them, I introduced a flow, and the way I introduced a flow is I asked you, because you are smarter than me, to come and tell me, give me a flow. So, you gave me a flow and I just verified those things, right. I just need to sit and verify that the function you have given me satisfies these things. I say, okay, I know it is a flow, and if you ask me how much is going through it, I simply calculate this. So, now that you have given me a flow, my question to you is, given a network and that flow, when I produce the residual capacity network, how many additional edges can I add? At most the number of edges. So, this will be just 2 times the number of edges, and once that happens, it is never going to go beyond that. Okay, so, it is bounded. Producing a residual capacity network is just going to have at most twice the number of edges. also for pairs of nodes which do not have any links to begin with, will not have any links. So, now this is how I produce the max flow. I start with a network, I just find some way of introducing a flow. Once I get that flow, I just produce myself the residual network. I take the residual network, I introduce another flow. Do not ask me how I am introducing that flow. I get that, I get another residual network. I keep doing this until I cannot find a flow. I stop. This is called the Ford-Fulkerson method. It is not an algorithm simply because it does not tell you how you are going to find a flow. It simply says find a flow, produce the residual network, find another flow, produce the residual network, find another flow, produce the residual network, and so on and so forth. Depending upon how you find these flows, your algorithm is going to be different, but the technique is called Ford-Fulkerson. So, okay, this is all there is. I repeat that. Good question. Why is this the maximum flow? What if you get stuck? Right? Stuck at a local minimum. Very good question, right? I mean, you start with a flow, you keep augmenting it until you cannot augment it, and I am saying that you stop there. There is no reason for you to believe, one, that it is a maximum flow, because maybe if you had done something else, you would have produced a larger flow. And two, what is this augmenting path business? So, remember what I told you is essentially start with a network, find a flow. Do not ask me how you are going to find a flow. Well, they are saying, well, find the simplest possible flow. And the simplest possible flow is not to try to send things in all directions. It does not matter. Ford-Fulkerson is basically saying if you are going to come from the source and send a lot of liquid this way and that way and try to get it out from the other side, do not bother, because you can do it in stages. You are doing things in stages anyway. So, what you should do is not try to find a flow that goes every which way. Just find a single path from the source to the sink and just find a flow through that path. So, if I found you a particular path with a bunch of capacities, what would be a standard flow that you can immediately send through this path? The minimum. Okay, so, you find a single path, you have a bunch of capacities. Remember, these are all residual capacities sitting there. You find all the capacities, you just scan through them, you find the minimum and say, I can immediately send through this minimum. Okay. The reason for that is that the minimum flow will be less than each individual capacity link. There is no other flow you are sending any place else. Only on these links you have a reverse flow, and the reverse flow is the negative of the flow that you have just sent in. That is a negative number. Each back edge is either a positive number or 0. So, a negative number does not destroy your capacity constraint. Mind you, you have to make sure that everything here is satisfied. So, essentially once you get a path, you find the smallest link capacity and just send that instead of doing it every which way. And the reason for that is you will find a path, You will take it out, you will find another path. So, essentially you are doing it in stages. Once again, it is an incremental way of pushing things up. But it still leaves this big question, which is, why is it that when you cannot do this anymore, you are claiming that you have managed to push the maximum flow through the network? Because what you did is, in some sense, a greedy technique. You could have been trying to optimize for each individual flow. It turns out that's a bad thing. Okay? But it turns out that if you close your eyes and just look for paths from the source to the sink in your residual network and repeatedly just send in a flow through it, you will end up with a quantity which turns out to be the maximum flow. That needs to be proved. You cannot just say that I did it and I got stuck, because there are various cases where you get stuck in local minimas. What happens essentially is that I will show you a proof that actually, if you look at it very carefully, and it won't show in the proof itself, the skew symmetry essentially allows you to push things back. So, it is the flow that you are setting up is not of a kind where you cannot backtrack. And the skew symmetry actually allows you to backtrack through getting stuck in local minimas in some sense, until you cannot do it anymore. But the way we will prove this thing is from a completely different point of view. We will claim that if you hit the maximum flow, then there is something called a min cut, and on that min cut there is as much that can be sent. And I will show you that all of this fits into that framework. But essentially what is actually happening is that because of skew symmetry, you are not sending in flows which cannot be backtracked. You can always reverse flows, and that allows you to get out of local minimas if there are any. The proof is, however, very different. So, let me start with a bunch of theorems or lemmas. It says something which is not obvious, but is what you really want. So, what this thing is saying, and you know that intuitively this would be the case, otherwise you would not have this incremental way of doing things. What this is saying is that assume that G is a flow network. Let us say F is some flow on it. Okay, so, you have a flow network, you put an F flow on it. Because of F, you now have G subscript F be the residual network. I am claiming that if you take this residual network and on that you can produce a new flow F prime, then if you look at the sum of the two flows, and how do I define the sum of the two flows? I say the sum of the, this is the mnemonic for the sum of the two flows, which is essentially from U to V simply add F and F prime. I claim that that itself is a flow, and it is a valid flow in G. Yeah. sorry, it is F plus F prime. In other words, if I have a flow in a graph, if I produce the residual network and can find a flow in the residual network, what I actually have is the sum of these two flows on the original network. So that the next time I make the residual network, I essentially can see it as a graph G with a flow F plus F prime in it, from which I produced a residual network. Do you see that? This allows me this incremental way of moving forward. But this needs to be shown. Okay. Intuitively it might make sense, but because you have constraints out here, what if some constraint is broken? So, mind you, whenever I say that F is a flow, I simply mean some function that satisfies those things. It satisfies 1, 2, and 3, and I know that if it satisfies 1, 2, and 3, I can calculate this, and that is going to be my flow. I do not really care about looking which way things is going. I simply go and look at each link. I say it is satisfied, the capacity constraint is satisfied. I go and see FUV, FVU. I find it skew symmetric. I go to every node other than the source and the sink. I see that flow is conserved. I am happy. It's a flow. Okay. So, in order to prove this, we know that if F is a flow, F satisfies all of those things. If F prime is a flow in GF, it also satisfies these things with, of course, with this being replaced by the residual capacity. My question is, if F is F plus F prime still a flow? To prove that F plus F prime is a flow, I have to see whether they satisfy those constraints. Okay. So, let me go and immediately pick out the trivial things that need to be shown, the things that can be shown trivially. I claim that 2 and 3 are immediate. Why? I claim that for F plus F prime, I am trying to prove that it is a flow in G. I claim that F plus F prime immediately satisfies 2 and 3. Why is that? Yeah.
Divide the defining equation by -1, and you get the constraint for the left hand.
So, this is defined as that, and I claim that that is immediately skew symmetric and has flow conservation on G. Why? F was a flow in G. It was skew symmetric. F prime is a flow in GF. It is also skew symmetric. If you add two skew symmetric things, can you get something other than a skew symmetric thing? You cannot. Okay? So, 2 is very easy to show, simply because this is skew symmetric, that is skew symmetric. So, the sum of those two will be skew symmetric. 3 is also trivial to show, right? This was conserving for all nodes other than S and T. This also conserves for all nodes other than S and T. You sum them up, you cannot get anything other than a 0. Mind you, these two things have nothing to do with capacities. Capacity does not play a role in these two things. These are the definitions that we have to have things working for us. Only thing we need to show is one. Capacity constraint is where the capacity really comes in, and now I have two networks, the original network, the residual network, different capacities, all of that stuff. But otherwise, once you take one out, 2 and 3 are just about flows themselves. So, 2 and 3 are done, trivial. All I need to show is 1. And 1 is also very easy, because this was satisfying the capacity constraint to begin with. I have f of u comma v less than equal to c of u comma v, right? And I have Cf of u comma v is by definition c of u comma v minus f of u comma v. This is by definition the residual capacity. I also know that the new flow in the residual network, which is f prime, is less than equal to Cf of u comma. And immediately you can see the result, right? F prime is less than equal to Cf. Cf is essentially C minus F. So I can replace that with C minus F. And I move that to this side. So I get F u v plus F prime u v less than equal to C u v. Simple algebra. And that is by definition my new flow. So the sum of these satisfies the capacity constraints of the original graph, which is essentially what we were looking for. You take a graph, you put a flow on it, you get a residual, you put a new flow on it. It actually corresponds to the sum of this flow and the previous, simple sum, element wise sum. If you sum those two up, that essentially is a flow in the original graph that can then give you a new residual graph. If you put a new flow in there, you can just put it back on the other side and get a new residual, and so on and so forth. This theorem basically allows us to say that every time you add a flow to a residual network, it corresponds to pulling it and putting it in the original network and having a new residual. Clearly, because this is satisfied for any flow f prime, I have shown you that the augmenting path and a flow on the augmenting path is a valid flow. So, it is satisfied for that too. So, Ford-Fulkerson essentially does produce UF flow. Agreed? Mind you, there is a difference between me just saying f prime be any flow and Ford-Fulkerson. Ford-Fulkerson says look for a simple flow in the residual graph. Just find a path, take the minimum capacity, make f between every edge to be that minimum capacity on that path. For every other pairs of vertices, flow is 0, and for the reverse vertices here, make the flow the negative of the flow that you have just put in. So, it is a very particular way of putting a new flow in your residual network. And because that is a flow, it is an f prime. The f prime here is very general. The f prime in the case of Ford-Fulkerson is a specific flow, and it still satisfies this. Any questions so far? Okay. So, what we have managed to show is that Ford-Fulkerson in this incremental manner is going to get you a flow. At every stage, whatever is being done, it can be added back to the original flow and it will remain a flow in the original graph, which will then have a residual capacity. So, this thing of taking a graph, putting a flow, getting a residual network, putting another flow, getting a residual network, and so on and so forth, can be seen as repeatedly adding flows on the same graph and getting these residual networks as a result. What I haven't shown you is that by doing this process, even though it is a flow, there is no guarantee that it will be the maximum possible flow. That when I come back, I will show you. Okay, so, let us take a break. I will come back and show you that this, the end result of this has to be the maximum possible flow.